So this is forest and box plot and whiskers plots, a brief introduction. This is a broad overview. This won't make anybody an expert, but hopefully it will at least demystify some of the things for us. And we are going to do a little poll with this. These workshops are organized by librarians at osteopathic medical schools to help you advance your research skills and support you in your scholarly activities. And hopefully they're a little entertaining too. So you learn something and have a little fun in about 30 minutes. So everybody's welcome. We would like to have all the participation we can. We've got some objectives here, just some basic stuff, because this is kind of dense material. So we're going to break it down, and I'm going to try to be fancy this time and use a little pen that's in PowerPoint. So hopefully that'll work out. Please do not criticize me for my drawing skills with a mouse. As y'all all know, that's not easy, but we're going to give it a shot and see how it works, because this is a safe place or safe space. So y'all can let me know whether you like the using the pen or not. So we're going to look at the basics of a forest plot. We're going to try to understand box plots, and we're going to try to figure out what those whiskers represent. And it looks like we've got some faculty, staff, bunch of librarians, and some other. So that's very, very cool. All right. We will start with forest plots. Now, generally, you will see a forest plot as part of a meta-analysis in a systematic review, right? And what a forest plot does is it takes the studies that are asking the same questions that you have picked from a systematic review and kind of puts the statistics and results on this axis. So it makes a visual representation of those studies. And it just summarizes the elements of these pooled studies. And it's also called a blobogram. So I guess forest plot sounds a little bit more official than blobogram, but yeah, made up word. Let me tell you, look, statisticians, all these people, they make up all kinds of words. So, you know, if it doesn't look right, if it feels funny to you, if your gut's telling you those numbers seem weird, you know, we're all intelligent people here. We all know when things look funny. So if it looks funny to you, even though somebody has presented some fancy looking statistics in a nice, pretty graph, if it seems odd, trust your gut and go a little deeper. Okay, so these forest plots have like a ton of little shapes. And so the first thing we want to do is kind of get a kind of idea of what all these little shapes are. So in a forest plot, you will have a point estimate, and that point estimate is the mean or the average, right? So it's either represented in a dot or a square. And then the whiskers you see, that's the confidence interval. And we're going to see why this is important. Now, the vertical axis is going to be the line of null effect. And I learned it as the line of no effect. So I call it the line of no effect. You can use either, whichever way you learn it. And then the horizontal axis has a number and some statistics, the things that are being used or measured. So those are the basics. And there's Kevin Jr. there, and that's kind of what he does when I start talking about statistics. But he's a good listener. Now, the most important part of a forest plot is this diamond right here. So this diamond, it kind of represents the point estimate and confidence intervals when all of those studies are combined. So the width of the diamond is the confidence interval. So the diamond here on here, that's what you want to see, because it's nice and it's short. So that means the confidence interval is narrow. And then all that vertical line is right there. This vertical line is just the mean. So if you see a diamond like this, that means it's got a wide confidence interval. So that's, if you remember from the last lecture, a biostats lecture we did, the confidence interval is where the statistician or researcher are saying that they think that the results will follow within this particular range 95% of the time, or whatever they set the confidence interval as. They can set it as less than 95 or higher if they're really, got a really good study going on. They can set it at 99 if they want, but generally you see it as a 95% confidence interval. So like the shorter one, the researchers could be saying something like, we're 95% sure if you reproduce this study that the true thing, the true amount will be between 1 and 5. So it's narrow. And so if you got a long one, they may be saying that we're 95% sure that the true amount is going to be between 1 and 100. So you can kind of see how that works. You want that narrow confidence interval, just gives you a little bit more confidence with that kind of thing. Okay. Now there's some advantages to forest plots. They improve precision with an increased sample size. So the confidence intervals should get smaller when you have that, right? So they can also answer questions not asked by individual studies, right? The point estimate is more likely to represent the true mean, and they can help settle conflicting claims because you will take, ideally, when you do a systematic review and a meta-analysis, you are going to have a collection of really good RCTs that ask the same question, right? So it's only as good as the studies that are included. But if you have a bunch of different articles, and I got a great example of this, you're going to love it. If you have a bunch of different articles about the same thing and they kind of have different results, you can take those articles and put them in a meta-analysis and systematic review and kind of see, when you take all those articles together, what does the evidence say? So it increases the power to detect clinical importance. Now, there's a disadvantage right there. Like I said, they're only as good as the studies included. They can be misleading. They are subject to a number of different kind of biases, but the main bias that we see is publication bias. And there are ways to test for this. And if you have a systematic review with meta-analysis that does not test for publication bias, because there's a special test for that. And we can look at that if you put that in the comments, you want to know how that works, we can do a snippet on that. But there's a test for it. You want to see that the authors have addressed it and done that test. So here's a real life example of publication bias. This is one of my favorite articles to give to students to look to see what a systematic review and meta-analysis should look like. And so what these authors did is they looked at the published research for reboxetine to see what it said, but then they went back and they looked at the unpublished research, right? And so when they did that, because the published research said that reboxetine was good, it was better than placebo and better than some of the other antidepressants. But when they did the research with the unpublished research, they found that overall it's ineffective and potentially harmful. So this is why we want to be careful about publication bias. You want to see that publication bias is addressed, because the tendency is for only positive things to be published. And I got a question here that says, where do you find unpublished research? And you have to dig. Then that's what we call the gray literature, right? So Google conference abstracts, government documents, and sometimes you have to go right into those companies like these folks did and get those internally published or not published, but internally completed studies, which, sometimes they don't want to give up, but they worked really hard. You can take a look. This is open source journal right here, or this article at least is open source. So you can take a look at it, and it is really nicely done. I kind of use it as my example, as just they did a great job on this. So when you take a look at this study, I'm just going to show you this. Don't let this overwhelm you. We're going to have simpler examples, but this is one of the forest plots from that study. So they have more than one in there. So this is how complicated and dense a forest plot can be. But this centerpiece right here, is a graphical representation of all this other stuff on the slide. And so this is what we're going to mainly concern ourselves with today. What all these things mean. So we're going to look at a little bit more of a clearer sample. All right. So we have this systematic review right here, and they're looking at foods on LDL cholesterol levels. And this is really neat. So we're looking at forest plots on the effect of coffee intake on LDL cholesterol. All right, so here's one of the forest plots right here, and we're going to take a look at this for a second. So generally, these things are divided into 4 parts. So this first part over here is just the list of studies included, right? They just list them. Now, sometimes if they have a whole ton of studies, or if they just want to, they may assign it a number instead of using the name and the date, but generally you see the name and the date. And then this information right here, right there, is the information about the individual studies, right? So you got the mean, the standard deviation, the total number of participants, that sort of thing. And then the weight is the weight that the authors, clinicaltrials.gov is great to find things that aren't published yet. Good suggestion, Dan. All right, so this weight over here is the weight that the authors have given each individual study. And you'll notice they make these judgments here based on sample size, whether or not they think there's bias in there, different things like that. So they'll be weighted differently, just depending on the confidence interval, those kinds of things. And so, but all of this is represented in this forest plot. So this is interesting. So here's our little dot. This is our point estimate. This represents the size of the study. So there are 58 people in this study. So that square is going to be bigger than the square that had the 15 people in it. And then the whiskers are is a confidence interval. So if you remember, we want a short confidence interval. So we rather this look like this, big with a short confidence interval. So we know that that's pretty good. That's a good study, and it would be weighted highly. And then what happens is they come down here and they total it all up. So they got the total, they check for heterogeneity, which is kind of a different topic that we could talk about, but basically this accounts for the differences in these samples. Each one of these samples is going to have different characteristics. So they kind of do some statistics here to address that issue. And then we have an overall statistic for all of these studies put together. And we can see here that the p-value is above 0.005. So we know that this study right here showed no statistical significance. But we can also know that this study showed no statistical significance because of this line right here. So this is our vertical line of no effect. So basically, if this diamond crosses or touches that line, you can tell right off that this shows no statistical significance, which is pretty cool, right? And the same thing goes for this study. This study showed no statistical significance. None of these showed any statistical significance between filtered coffee and no coffee and changing LDL levels. Isn't that pretty cool? I think that's pretty cool. All right, let's look at one more. Here's a little bit simpler one. This is between coffee and tea. So we've only got 3 studies here. So, this is not very powerful. And we really only have, we got 100 samples there and 82 samples there. And again, we've got no statistical significance, but we know that because even though it's just right there, our diamond is touching the line of no effect. So we know that there is not statistically significant. One more. All right. So this one, what do y'all think for this one? Got the answer down there, but this one does show significance. Look at that. So what they found in this study is that right here, drinking unfiltered coffee does affect your LDL cholesterol. Isn't that wild? But you can tell they've got this study weighted high, and it's got a pretty short confidence interval right here. And then we got a small one with a wide confidence interval that touches the line of no effect, but the rest of them don't. So this is pretty strong right here that you want to drink filtered coffee rather than unfiltered coffee. And that's all there is to it. So are there any questions about that one? About the meta-analysis, the forest plot, before we go to box and whiskers? It's just a nice visual summary. Now, the main thing, remember, and the main thing I tell my students is that, again, this is only as good as the studies included in it. And if they don't include, or at least address, the effort to find gray literature, that makes me wonder. And if they don't do the test for publication bias, then that makes me wonder too. It just makes me want to dig a little bit deeper to make sure that what they're reporting here is accurate, or as accurate as it can be. All right. So now we have box and whisker plots. And that's kind of how they make me feel sometimes. And these are kind of simpler. These are much simpler. So they're just used to show the distribution of data points across a measure. All right. So we're just going to have displaying the ranges between variables. We're going to have the outliers marked on them, the median mode where the most data points are in the box. And it's going to summarize the data in 5 marks. And it just shows a distribution. There'll be 4 sections. And each of those sections are going to contain approximately 25% of the data in that set. So what these do is you run a box plot and you can easily see the mean values, the dispersion, and if the data is skewed or not. So if you have multiple, if you're looking at multiple groups or multiple things, it's easy to use a box plot to see the differences in these samples or groups. Okay. Now, these are great to use like test scores between groups. Like if you wanted to do, like we have our students here divided into small groups. If we wanted to see test scores between these groups, then this is a great way to do that. If you want to look at data before and after some sort of change or intervention, that's great. Another example I found that made a lot of sense was, heart rate comparison for resting, walking, and running. And this is just, this box plot just is a really basic overview of the data, and it just gives you clues whether or not you want to look harder at something, because we've got some limitations here. And so these limitations, they're very simple. They don't show the density of the data. They lack detail on the shape and the distribution. Like if you have a big old peak in something that might be interesting or significant to you in your research, then this is not going to show that. So what do these look like? So this is what they look like. And we've got a lot of terms for this one. This one's got a ton of terms. So we've got the minimum score, which is down here. This is the minimum score right here. This is where the first quartile is right there. So that's 25% of the scores or data fall below that. Then we've got the median. That's important. That's where, that's the halfway mark. And we've got the third quartile where 75% of the scores fall below the upper 25%. And the maximum scores over here. We got the maximum. I don't know what happened to my word max, but we'll put them back right there. And then the whiskers represent the outside middle, I mean, the outside, excuse me, represent the outside middle 50%, right? And then these are outliers. So you can see your outliers on there. And if you remember, if you don't watch and deal with your outliers appropriately, then they can really skew your data. And one good example of this is if you took, and I'm just going to make this up, if you took all the salaries of the general working population of Apple, and then you just put in Bill Gates's salary, whatever it was, his salary is going to make all those other salaries, it's going to skew it so they look like they're paid more. So you have to be careful with your outliers. And then this right here is the interquartile range. Y'all know I have trouble with those R's and S's, right? So they show the middle 50% of the scores. If this sounds familiar to you, kind of like what a bell curve might show, yeah, it's similar. Okay, and I've got another visual right here that just kind of breaks it down a little bit. This is from a complete guide to box plot. It's in my references. This is a really, if you want to really take a deeper dive, this is a really great website for that. But this kind of shows you the first, second, third, and fourth quantiles right there. Okay. Now let's do a scenario. Let's do an example. Y'all love this. So we have a coffee shop owner that wants to track the number of orange scones sold during the week, because who doesn't like an orange scone? So we got to have some data. So here's our data. So the first thing we're going to do with this data is we're going to put these numbers in ascending order. So there they are. So we got 5, 15, 19, 25, and 32. Okay. So what we're going to do first is we're going to identify our lowest number and our highest number. Then we're going to identify our mean. So we've got the lowest, the highest. So this is the 5 will be the end of the whisker. The 32 will be the end of the upper level whisker. And then our median right there is going to be our center. And then what we do is our upper quatrail, and I think I'm saying that wrong. I think I've got a little issue today with my letters. And then the lower quatrail, and I got those reversed. But anyway, so what we'll do next is we'll put them on a line. So here we go. We're going to put the lowest there, the highest there at about 32. We've got that lower, sorry about that, quatrail right there at 15. He should be directly over 15. And then the higher one is 25. And then the median is there in the middle. So then what you do to draw your box plot is you're going to draw the interquartile range, right? And then we've got the median right there. And then these are our whiskers. So this kind of tells this coffee shop owner how many scones to make during the week to have enough right here, you know, to make between 15 and 25, and she should be okay. Now, this is a very simplified box plot and whiskers, but if you did this over the course of a year for your orange scones for every month or every week in a month, then you could really see what months orange scones seem to sell the most. And so then you can buy the supplies for those during that time and, you know, save yourself some money and be more efficient. This also works well with salaries. You can kind of see, I saw an example where they had what basketball team paid the most, and that was very interesting. And then the heart rate one was interesting too. So that's kind of the basics of forest plots and box plots. And again, the takeaway is that they're just a visual representation of data. So if I saw this and this was, the median was way over here and it was skewed way left, and I'm like, I need to run a more sophisticated test to see what's going on with this data right here. Okay. So there's your overview. There's Kevin Jr. again. He says, drink filtered coffee and know things. And if there are any questions, I'll be happy to try and answer them. And then we've got references here that will be posted. You can go to the YouTube channel, pause it, get some good stuff here. I can recommend, Dr. Shadefeld has awesome stuff. All of these have really good ways to dig a little deeper if you want to. And then what we have are feedback. So please fill out the feedback form. Let me know if the pace was right, if you like the pen, if you want to dig deeper into box plots, forest plots, or something else, or any of the biases. Those are always fun to talk about. And then we have the next one is November 16th, qualitative research, which is one of my favorites. And you can register there on our calendar. Oh, searching for protocols for RCTs, yeah. That's a good topic. Let's see if I can drop. Let's see.
I'll grab that link.
Oh, good.
No problem. It'll take me just a moment to get to, though.
I'll go back to the reference slide. Yes, some of these are really good. This McLeod one, what does a box plot tell you? That's a good one. The Cochrane training is good right here. All kinds of cool stuff.